And the work with the layer right. And indeed, we worked on the problem when Kathleen was in Tel Aviv. And so it is essentially still a work in progress. And I hope you will enjoy it. So the talk is on stopping games. And we have a new feature in those stopping games, which is termination rates. I will explain everything here. Now, Ehud told me that the most important thing in the seminar is not to convince you that the results are very interesting or unique, but that you will gain something from the solve, that you will remember something. So I hope that you will remember two things from this. So stopping games are games where the decision of the players is when to stop. So the game goes on as long as nobody stops, and once at least one player stops, the game terminates. And the terminal payoff depends on who stopped at the termination stage, on the termination stage, and maybe on additional information that is revealed to the players along the way. So we have several classes of well-known games that fall into this category. We have preemption games, in which each player tries to preempt to be the first to stop, like patent races. We have wars of attritions, in which every player wants to be the last to stop, like wars of animals that are fighting for territory. And in option pricing game options, in which we have the issuer of the option and the buyer of the option. Usually the buyer of the option decides when to exercise it. In game options, the issuer can also cancel the option at a given cost in penalty. So those are few examples of stopping games. And the formal model, we have a probability space, so an underlying probability space. Then we have a set of players. So we will talk both about zero-sum games, non-zero-sum games, and also about multiplayer games. We have a filtration. The filtration can be either in discrete time or continuous time. So that depends if the game is in discrete time or continuous time. And the filtration represents the information that the players have along the game. So in every period, whichever whether it is in discrete or continuous time, the players receive some additional information possible about the payoff process. And then for every non-empty set of players, S, we have a payoff process, which is Ri valued. That is, this is the payoff of all the players in I, if the players in S stop in time t. And this is a process in discrete time or continuous time, depending on time. So is the model clear? So when I started working on stopping games, when I was young, I thought about the stopping game as a tree, an infinite, for example, binary tree. We start at the roots where we have the pair of if I stop alone, if you stop alone, both of us stop together, and then with equal probabilities move to this, to each child, and then again in each child we have the pair of each stops, and so on and so forth. So such an infinite tree is a simple example of a stopping game. What is a strategy?
So each player, individual player doesn't have it. What is the payoff for individual player?
My payoff, if I stop alone, is so XS is the payoff process if the players in S stop together. So if I stop alone, so the set S is equal to me, alone, contains a single player. Then the process x Eilon,
Okay.
which is the payoff to everyone. Eilon stops alone at time t. And then we have another process, which is x Yevgeny. What is the process? The payoff if Yevgeny stops alone at time t. Okay? And we have a third process, which is x of Eilon and Yevgeny. The payoff if Eilon and Yevgeny stop together. So if we have I players, we have 2 to the power I minus 1 non-empty sets of players, coalitions, and then we have 2 to the power I minus 1 payoff process.
Which determines the pair for each individual?
Yes.
Okay. So each one of them. Okay.
Yeah, it is high value. Vector value, right? It gives us each coordinate here is the payoff of each of us, whether I stopped or did not stop.
So if it's a continuous game, you still can have a situation which 2 players stop together.
Yes.
Because it's determined. It's not
Yes. If both of us decide to stop at times of 3, then we have a payoff, which is for all of us, which is the payoff is both stop at 3. So this is the data of the game. A strategy will be a stopping time. So it is stopping time adapted to the filtration, to the information that the players have each time. Okay, so each one of us decides when to stop. What is the information? The filtration. The filtration is what is the filtration? The sequence of sigma algebras, one for each key, and it is increasing. Filtration is always a non-decreasing sequence of sigma algebra. Sigma algebra is a partition of omega. This is a sigma algebra.
So this is the public signal?
Yes, this is the public signal. We all share the same information. So there is a recent work on stopping games with asymmetric information, a work of Ro'i Yakubovich.
So theta I, tau I is a function from what?
Tau I is a function from omega to a set of times, including infinity, because I can decide never to stop.
And random.
No, the stopping time, deterministic stopping time.
Right,
I
started.
Okay?
So how is it applied? How do you decide when to stop?
How it was. So
we don't know the state of the world. Right? We don't just know the event.
So a stopping time is a function tau I, my stopping time, from omega to times, let's say discrete time union with infinity, okay, such that, what does it mean that it is adapted in the stopping time? It is adapted to the filtration. It means that the set of all omegas such that I stop at time n is an element of Fn. Okay? So I know when I should stop. Okay, so this is the stopping time. Okay, so if every player uses the stopping time tau I, then the game terminates at the minimum of the tau i's, and this is tau star. So tau star is the time in which the first player stops, and S star is the set of those players who stop at time tau star. Okay. And then what is the payoff? The payoff given a vector of strategies tau I is equal to the expectation of the payoff process of that is determined by this the set of players who actually stop the termination stage at the time which is t equal to the termination stage. And this is given that the termination state is finite. So if the termination state is infinite, you get none. Okay. So this is the payoff in the key. Questions?
And it's measurable, the X, S star, tau star.
Yes.
Is measurable?
Yes.
You
So
have an additional assumption? Or?
no, those processes are adapted to the filtration. So this means that they are measurable. Okay, you are absolutely correct. You need progressive measurability.
That's for a fixed S.
Yes.
But next star is random.
Yes, that is random, but it depends on it is determined by the stopping times, which are themselves measurable with respect to the filtration. And therefore, this process is also, this function is also measurable with respect to the filtration. It's adapted to the filtration. So in continuous time, there are more issues, technical issues with measurability. And so you need to assume all the proper measurability conditions. So we do it.
If we discover one day what they are.
Yes, but I suppose I will tell you that you need that those payoff processes be progressively measurable. Great. I could even write down here what progressively measurable means. Great. Okay.
This is not one of the two things that we should remember.
Exactly. Yes. So there are technical assumptions on measurability that we need here. Okay, so we make it. Okay, in discrete time, all you need is that the processes are adapted, and that's it. Okay. Now here I assume that the payoff at infinity is 0. This is without loss of generality. The payoff, if you want the payoff at infinity to be any measurable function of omega, that's fine as well. You can incorporate this terminal payoff at infinity in the payoff process. So this is non-issue to be decided. Yeah, it will not be constant. Can be the payoff at infinity can be any measurable function of omega in any measurable function. It's fine. For example, just to convince yourself, suppose that time is 0 up to infinity. Now we don't have discount, so we can shift time, we can squeeze it, extend it, and we don't care. So squeeze time, so that is between 0 and 1. I didn't do anything so far, right? And now the payoff from time 1 up to infinity, whatever happens, is this terminal payoff. So if I stop alone, if you stop alone, if you stop together, the payoff is this terminal payoff. Okay, so whatever we do afterwards, the payoff is this terminal payoff. Never reaches it, because whoever stops before is fine, right? And anyway, whatever we do. Okay, so this terminal payoff is really not an issue. There are more ways to incorporate the terminal payoff in the payoff processes, but again, this is not that important. So this is the stopping game. And now you asked about randomized, which is randomized stopping times. So a randomized strategy of a player is a randomized stopping time, meaning a probability distribution over stopping times. So again, you need to do it properly so that it is measurable. So it should be a measurable function from the unit interval 0, 1, which is your coin, cross omega, to the times in which you stop, such that for every outcome of the coin, the section is measurable. It's adapted to the filtration, the stopping. Okay. So this is a random stopping. But anyway, probability distribution of the stopping time, this is fine with us. And now we can ask whether value exists, whether an epsilon-equilibrium exists. Okay. So those are questions that we can ask both in discrete time and continuous. So here is a slide with the known results on this topic. Okay? Merely existence. Once we know that the value that equilibrium of the value exists, then we can ask economically interesting questions like what is the structure of equilibria, who stops first, how does the equilibrium handle the parameters of the game. But first, the mathematician will ask whether there exists an equilibrium. So in discrete time, in the two-player zero-sum case, we have equilibrium, and this is a result with Dina Rosenberg and Clavier. And then in two-player non-zero-sum case, still in discrete time, with Schmeier, we prove the existence of an equilibrium. By the way, in all of these cases, we assume that payoffs are bounded. Because if payoffs are not bounded, well, then who knows, equilibrium not exist. We can always want to wait one more stage and get a higher. So payoffs are bounded. Okay, in three-player games, we can take the same technique as in two-player games, make it more complicated together with my PhD thesis, where I studied three-player stochastic games. You put them together, you work hard, and you get existence of epsilon equilibrium. And this was never published, but it's boring, just to find it. For 4 players, it is open problem. We don't know whether 4-player talking games in discrete time have an epsilon equilibrium. Continuous time. So 2-player zero-sum games, we have an equilibrium, a value exists, and this is the result with Ridal-Araki. And then 2-player non-zero-sum, epsilon equilibrium exists, still the result with Ridal-Araki. And then in 3-player games, continuous time, you have a counterexample. The value in stopping games in continuous time, 3 players did not exist. This is surprising. Value? Equilibrium, sorry, equilibrium. The epsilon equilibrium did not exist. This is surprising first because in discrete time we do have an equilibrium, but in continuous time we don't. So there is something in the fact that time is continuous that makes equilibrium exist. Second, whereas in discrete time games, this is a stopping question whether every stopping game has an epsilon equilibrium. In continuous time, we have another example. So this is so one thing I would like to take out of this talk is this counterexample. And what makes it work? So let's see the counterexample. By the way, multiplayer games. So Yuval, he proved back in PhD that there is a correlated equilibrium in stopping game, multiplayer stopping games in discrete time. There is a correlated equilibrium on this epsilon correlated. Okay, so okay. So let's switch to the counterexample.
What is the correlated? Because they have a public signal. So they need another public signal?
Yes, they need another public signal, which is public at the outset of the game.
It's not a public signal. The correlated.
Yes, sorry. Correlated equilibrium is a private signal. One is correct.
Which player?
Each player a private signal. They are correlated, those signals, but they are private. Sorry, I understand.
Which one of the are any of these also zero equilibrium?
No, all of them excellent equilibria. Because those are infinitely repeated games, right? And horizon is infinity. So we can always want to wait slightly more and get an epsilon more pair. So you cannot hope to get a zero equilibrium or a zero optimal strategy on the epsilon. Okay. So this is the example.
These are equilibrium mixed strategies.
Yeah, all equilibria are mixed strategies. So the theory in the 80s was done by mathematicians, from mainly French mathematicians, who came from control. And so they work on, and they still work, French community, work on few strategies. What are the conditions on the payoff processes that guarantee zero equilibrium or epsilon-equilibrium in pure strategies? And we have conditions on that. Okay? We are to do all those results, we prove them because nobody worked for us on stopping games with these strategies.
So the very basic law of attrition uses these practices.
Yeah, but those were very simple cases, not in for general stopping. So therefore there was a lot of place to work. Okay, so in the counter example, there are 3 players, and payoffs, there is no omega, no probability space. So payoffs are constant along time. So not only they are constant along time, and no omega. So just a set of players. And this is given by this intervention made. So player 1 chooses a row, whether to continue or to stop. Player 2 chooses the volume, is the blue. Continue to stop. And player 3 is the third player, new player, and she chooses whether to continue or to stop. So if player 1 stops alone, regardless of the time in which she stops alone, she gets 1, player 2 gets 0, and player 3 gets -1. If player 1 and 2 stop together, regardless of the time in which they stop, 1 gets 0, 2 gets -1, and 3 gets 1. Thanks. Now, so this is the game. Game payoffs are constant a long time, and there is no omega, no information about it. What are the features of this game that ensure that there is no epsilon-equilibrium?
So player 1 would like to stop immediately.
Yes, each player.
Each player would like to
Also,
stop.
player 2 also would like to choose to stop immediately, because if she stops immediately, she gets 1.
Okay,
And player 3 also would like to stop immediately, because if she stops alone immediately, she gets 1.
Then you pass some curve to the other people.
But there are no side payments.
Structure.
Yes. So if I stop alone, I get. So if player 3 stops alone, she will get 1, but then player 2 will lose. So whomever stops, she wins, but the one to her left loses. She's the.
One is B, one is C, one is E.
They are both all. Yeah.
That's not non-binary. That's continuous gender spectrum.
Yeah. So, what are the features of the game? First, the sum of payoffs is always 0. Right, so this simplifies the matter. We know that the sum of equilibrium payoffs is 0, everything always 0. Whatever they do, the sum of payoffs is 0. Second, if one player stops alone, her payoff is 1. So each player wants to stop because then she gets 1. But sum of payoffs is 0, so that I stop alone, then Omer will lose, and then he wants to stop before me, but then he can lose, and this will drive the contradiction, the non-existence of epsilon-equilibrium. Okay. So first they claim that there is no equilibrium in which the game stops in time 0. The first instance of the game stops. This never happens. Why? Suppose there is such an equilibrium. Suppose that player 1, then one of the players must stop with probability 1 at time 0. Suppose it is player 1. So player 1 stops in time 0 with probability 1. So then we are in the bottom 4 entries. So what will player 2 do? What is the best response of player 2? So player 2 compare those, if it continues, he gets either 0 or 1. And if he stops, he gets -1 or 0. So 0 is better than -1, 1 is better than 0. So that if player 1 stops with probability 1 times 0, then it is dominating player 2, stopping to continue. Okay, what will player 3 do? Player 3 will compare this -1 to this 0, and he will stop it. So player 3 will stop, and therefore we end up in this end. But here, player 1 gets -1, and if he continues, she gets 0. So she will not stop before 81, and therefore there is no zero equilibrium, there is no x small as well, they continue with the arguments. Okay. Fine. I showed so far that there is no equilibrium in which the game terminates in time 0 with probability 1. Good. So that means that if we have an epsilon equilibrium or an equilibrium, then the game continues after time 1, after time 0 in positive probability.
Each one is better off.
Exactly. But then each player wants to be the first to stop. Right? Because since the sum of pairs is 0, means that at least one of us, if the game did not stop times 0, at least one of us gets a non-positive payoff. But if I stop before you, I get 1. So I'd rather stop before you. Right? But time is continuous, so you can always stop before you. But each one of us wants to stop before the other. So there is no equilibrium.
Under continuous centipede.
Yes. Yeah. So the issue here is that
You just stop it by zero.
no, but we said we cannot do that. In time 0, the game already.
The best response, assuming that the game does not stop, somebody has a better response which is stopping it.
No.
No, one.
Suppose there is an epsilon equilibrium. Suppose. Okay. Then it does not stop in time 0. Now, in time 0, this is suppose the 0 equilibrium. Okay. Forget this. 0 equilibrium means I'm indifferent in time 0. You can stop it. So if I stop in time 0 or I continue, I get the same payoff. Okay. But then, if the game continued after time 0, the game did not stop at time 0, then in time, then right after, then my continuation of as we leave time 0 and look at the future, my expected payoff is non-positive. Because the sum of expected payoffs, continuation payoffs is 0. So my payoff suppose it is non-positive. Now I see your strategies, I know your strategies, you're in it. I know when you're going to stop. You have a probability distribution over when you are going to stop. But time is continuous. I can always stop before you. Right? And then I will get 1. So I will profit 1. Now I cannot stop at time 0 because we just left time 0. So I want to stop as quick as I can and get 1. But then the original strategy is not an equilibrium because I can gain 1 times the probability that the game does not stop at time 0.
What happens if we assume discrete time?
Discrete time no problem. In discrete time, in which you can symmetric equilibrium, this is a symmetric game. Symmetric games, there are always symmetric equilibria. Like it's not always, but in this case, there is a symmetric equilibrium.
In at 0, at time 0.
At each time,
If you left time 0, the next stop is time 1. You cannot start before time 1. That's the function.
yeah. That in discrete time, if we did not stop at time 0, the next opportunity to stop is at time 1. So there will be an equilibrium in which there is some probability lambda, in which each player in each time stops with probability lambda. this will be the equilibrium continuous in discrete time. In continuous time, it is not an equilibrium.
That's what I understand. So there is one of the players whose future payoff is less or equal to 0,
Right.
but still it is indifferent between stopping at time 0 or not. Because
The equilibrium. If we have an equilibrium, then you are indifferent.
right,
Between continuous and
so
stopping.
how come that it's indifferent at time 0? Because there is a probability that if it starts at time 0, other players also start, and therefore is okay, its payoff will be 0 again. Okay.
So, right. So this is the example for existence of the equilibrium. Okay, but I make my living from existence of the equilibrium. Okay, so this is not enough, right? So we need to change the model. So there are two ways. Either you change the equilibrium concept, then you look for like you got Heller, and you look for correlated equilibrium. Games in discrete time. Okay. Another option is to change. And this is what we try to do to and we say, okay, there is discontinuity. What is the discontinuity? If I stop, the game stops with probability 1. Terminates. That's it. If I do not stop, the game will not stop. So there is some discontinuity about the behavior. So what happens if we add termination rates? So that even if I want to stop, the game does not necessarily stop with probability 1, but only at some rate in continuous time. So in each interval delta t, there is a probability which is a something times delta t that the game stops. So this is what what our idea was.
Unless everybody does it.
Yeah, if nobody presses the button, pushes the button, then the probability of stop is 0. Okay, so let me introduce then the model, and we will see whether.
And we can adapt it further. So if somebody presses the button, it will stop, but the time.
Let's. So we have the same stopping gate, but I add additional processes, which are the termination rates processor, which for rates, I call them row of the set of players who stop, who press the button, and so for each set of players, for example, for me alone, there is a process row of Eilon. So if I press the button continuously, only I press the button continuously, then in each interval of length dt, the game stops with probability which is row of Eilon time t dt.
So if other people push the button during this interval, what happens?
Yeah, so if Yevgeny and I push the button together along the time, then we have row of Eilon and Yevgeny, which is not necessarily row Eilon plus row Yevgeny. No. So if for some interval of time I and Yevgeny push the button, then we are absorbed and we terminate at a rate which is according to row of Eilon Yevgeny. Then at some point, Yigal joins us, and then the termination rate changes row of Eilon Yevgeny Yigal. And then Yevgeny drops, stops pushing the button, and then the rate of termination changes to row of Yigal and Eilon. And so
And do they see
yes, we see each other. We will talk about what we see.
Then you press and then unpress.
Yes, you press and then unpress, press, unpress.
Not here, not press and everything.
Also, we talk about observation, but in general, yes, strategy depends on as a usual in the repeated games. I observe what the others played in the past.
And the last point, they push the button in the time interval, they push a T, no?
At time t, in the time interval t plus delta t, we push the button, I and q.
There's a comma. The button comma in the time interval.
In the pairs in S, push the button in the time interval is, then the game terminates with probability this in that time interval. Okay, so this is continuous time.
It's there, where is it there?
The then is here. Then the game terminates. Okay, so what you actually do is you write down the formula, the integral of F's. Okay, and this is how you, this is just the verbal interpretation of the termination rate, so that we can understand what it signifies. But down to it, we have a formula. Okay, that if this is the rate in which the process terminates, then you can calculate the probability that for every strategy profile, we can calculate the probability that the game terminates by a specific set of players up to some time t, okay, which is an integral of something, and then we can calculate the expected payoff, and this is the expected payoff in the given the vector of star.
If I push the button for like 1 second, and within that second, each instance, it terminates at
Yes.
row wherever
Yes.
half second.
Yes.
Stop.
Yes.
Strategies are pretty complicated.
Yes. Strategies are complicated. Why? Because in a standard stopping game, your strategy is when to stop, and that's it, the game terminates. You don't need to think what will happen after you stop. Here,
Should be measurable.
yeah,
Measurable.
yeah. So here, I press the button, then the probability that the game terminates in the first instance in which I press the button is 0. Okay, so my strategy should be a function right from time, and then it should be measurable, of course. It should depend on the past. So it is a quite involved object. That's true. Okay, we will talk about strategies in a moment. That will be something like showing them something about strategies that I hope that we will take from this talk as well.
So,
Instead of pushing the button together, two players can push them at random times, like crazy, really crazy, and then you get the distance.
Yes, but you need to do it measurably, right? You cannot do measurably. Okay, it must be intervals. So in a short interval, I stop alone, then in a short interval, you stop alone, and if the interval are really short, then because termination is in continuous time, then it is as it is. Right, you're absolutely correct. You can do that.
you can think of the history of the function from time to the set of coalition, possible coalition.
Yes. But okay, also the question is, do I see your actually when you stop, when you press the button, or only the rate when you press the button? We will talk about it in
What do you mean by the rate?
okay. We will in a moment we will talk about that. Okay, so what is a control? A control essentially is a behavioral strategy, a behavior, sorry, not a behavior strategy, behavior play in continuous time. So a control of player I is a measurable function that for a measurable process that for every time t, it gives me a probability distribution in 0, 1. This is the probability that I press the button in time t. Okay? I need not play a pure start that either presses the button.
By measurable, you mean measurable with respect to the development of the time, or measurable with respect to the filtration?
So it should be measurable both with respect to the filtration and with respect to time. Progressively measurable, this is the code. Okay, but it should be measurable.
For every time t, there's a probability.
Mhm.
Separate probability to each time.
Yeah, for every time t, I have my probability, press the button at time t. Okay, and it is a function of omega, and then it is measurable with respect to my information time omega, and measurable with respect to time. So this is this process, the control, my control. And I
But
will-
if it's zero all the time, can it be bigger than one, the integral? I mean,
if I
at each point, it's between 0 and 1, so it might be 0, but the total can be positive, no? The probability of pressing the button.
if I press the button, it will be 0 always. Then
It's
the
like a
integral-
density function, no? It's like a density function.
Yes, this
So if you take the integral, it can be 0, no?
the integral if ui can be positive on a set of time of measure 0, and then it is as if I didn't press the button, right? Because the probability that I press the button is 0.
It's not about the assumption of whether I press the button.
This is whether I press the button or not.
Let's say, if I say, really half I press the button, if this probability will be realized, then we will do something.
So this is the probability I press the button in time. Okay, I don't think about realization. Okay, because if we have such a thing, then you have continuum of independent random variables. You don't want to get into that. Okay, so this is the probability that I press the button each time, and then the total probability that I press the button is the integral of the.
So what does it mean? If the probability is 1/2, how do I do that? At each time I press the probability 1/2. How is that actually accomplished?
How do we
Either press all the time, or not press it.
no? So assume it is pressed as if it is pressed IID. But as we know, there is a problem, a mathematical problem in pressed IID in continuous time. And therefore, what we do is we simply write down the mathematical formula, and if you could press the button with probability 1/2. Okay, now you would say, okay, so you have a nice mathematical model. What does it represent in real life? So I will tell you, okay, does continuous time represent in real life when time is actually discrete? Time is discrete.
Time is continuous, that's what they.
No, it's true, but something.
Well, then they change the theory and the
Okay. So that will tell you, suppose that time is discrete, but it is very fixed very quickly. So you, as a boundedly rational person, okay, you cannot actually press the button half hour. So what you see is the averages. Okay, you know that in some short time interval, I press the button half the times. And when you move the time interval, you observe that I press the button different frequency. So what you see are local frequencies. And this is those. So this will be my practical story behind this mathematical definition.
It's similar to this idea when you say, now I press the button for a certain amount of time. So each time I press the button, I also have to say for how long.
No, it is completely different. For example, because the payoff processes are do depend, do change differently. So I don't think it's.
Still don't understand how you have IID continuous over all of the time region or all time.
What do you mean? You do not understand how I can help? Mathematically, I don't.
Exactly. So how do you deal with it?
So I provide the definition. So I calculate what I should give you is for every vector of strategies, or controls. Well, to define a game, we need to define the set of strategies, controls, and pairs. That's it. What is the interpretation in your mind? It's your problem. Okay, I need to convince you of this, but study, but whether it is convincing or not, this is subjective matter.
Then they are a pure strategy, but when they press the button, they press it really hard or so.
I didn't understand that, but they can like the break.
The full rate.
Yeah, that's true. So this is an extra application, but then the question still would be, what does it mean in continuous time? I press the button softly up to 0.5. What does it actually mean? It means that my something the thread stops.
Can you think of it as a distribution of stopping the distance or something?
Yes, you can think of that this way. Yeah, that every control
Something like the break, right? Some probability of stop, some probability of stop.
yes, so every set of controls finds a probability distribution over the stopping time, and then you can say that you actually this is what you want. But the problem here is that this every vector of controls finds when we stop. All of us. So
to go back to my question because I didn't get it. So if I have a uniform distribution over 0, 1, the time between 0 and 1. So at each point in time, as soon as it's a uniform distribution, it's stopping time. And I'm gonna stop at some time. So it's not uniform, but some continuous distribution of 0 to 1. So at some point, for sure, I'm gonna press the button. But at each point in time, my probability to press is 0.
that's true.
Right? So it might be that the probability at each point in time is 0, but the sum is positive.
That's true.
That's what my question is.
That's
Okay,
important.
it's possible. Okay.
Yeah. But in the original model of standard stopping games, then actually, whenever you press the button, the game stops.
Right.
Here, no.
Here you can continue.
Yeah.
Okay.
Okay. Now, this is a control. What is a strategy? My strategy is not simply a control, because a control doesn't look on the behavior of other players in the past. Now, as we know in computer time, we have to be careful about whether strategies define the play path uniquely. Right? Because if you are not careful, then there are several play passes that respond to the same strategies. Right? For example, we can both continue, we can all continue in time 0. And then afterwards, my strategy is I look at you. If you stop in the past, then I stop from now on. And if you continue throughout in the past, I continue in this time instance as well. So for those, if all of us use this strategy, then there are two play paths that are consistent with it. One is that we always continue. One is that we all stop after time 0. We all press the button after time 0. So we have to be careful defining strategies into this time. So that the play path is uniquely defined.
You start stopping.
Yes. Yeah. You can also start stopping after time 1/2. That's true.
Makes it even worse.
Yeah. Anyway, we have to be careful. That's the point. And so the way that the French community deals with it, and this is the standard way, is to define non-anticipating strategies with delay. What does it mean, a non-anticipating strategy with delay? It means that Eilon, I divide the time into the time space, 0 up to infinity, to pieces, countably many pieces.
It's equilibrium or 0, 1?
Yes, it is zero infinity, sorry. Okay, because time is zero up to infinity. So, and therefore it is not finitely many, but I mean, each time interval 0, 1 is divided to finitely many subintervals, so that all are divided into countably many intervals. And at the beginning of each interval, I look what happened in the past, and then I determine what to do in the next time interval, in the next element of the partition. Okay? So this is the strategy. The strategy is a partition of 0 infinity to countably many consecutive intervals.
So the partition is part of the strategy, and it's not adaptive.
Yes, the partition is part of the strategy. It can be time dependent, can be adapted to the past. It doesn't really matter. All we want is that it will not converge finitely, but it will eventually go to get you.
Each player has its own partition of
Each
that.
player has its own partition.
So it's determined by the controls of the others.
Yes. Yes.
They overlap.
Yes, partitions can overlap or not overlap. Depends on each one through his or her own partition. And at the beginning of each element of the partition, we have a function from past controls to my control in the next element of the partition. And I think you can see that this actually well defines uniquely a play path.
Is this the same as in stochastic game or did? The same
The
concept.
same concept as in there. This is the standard concept of strategy in continuous time. Okay. So this is strategy, and then we can ask whether an equilibrium exists with this type of strategy in our class of fields.
You have to tell us what the payoffs. What is
The payoffs? The payoffs are as in so we have a payoff process, we have a termination rate. So given strategies for every vector.
I still waiting on top.
Yeah.
What is the goal to use and what is the set of players to stop?
Okay. So that so if we have every vector of strategy uniquely determines a vector of controls to each one. Right. So in the first time interval, it is simply my control in the first time interval. Then at the end of time interval, I look what you play in the past, and I determine my control in the next time interval, and so on. It's profile of control.
Profile of vectors. Profile of vectors.
A profile of controls, a vector of controls, one for each player.
Right, it's a vector of control.
Yes.
And it's profile of vectors.
A vector of controls. Profile and vector is the same thing.
Same.
Yes, each player has a control, so that together we have profile of controls or vector of controls. Now, given the vector of controls, we are going to write down the expected payoff as if those controls were played in continuous time with independent story. So that in each time instance, I play my U of T, and Ron plays his U of T, and Shiri plays her U of T, and so on. So then we can ask, okay, suppose that in that time interval, I play my behavior, I mixture U of T, Ron his U of T, we have a probability distribution over the entry of the matrix. So we have the probability that in that time instance, we stop together, each subset of us stop together. And then I take the integral of that. So this is a mathematical formula that treats our controls as independent over time.
There is also the row of
Yes, so you have to multiply it also by rho.
each row.
The rho for each subset of players, Shiri and me, we have my U, the probability that I stop I press the button at time t, times the probability that Shiri presses the button at time t, times the probability that you do not press the button at time t. This is the probability, the instantaneous probability that Shiri and I will press together the button at time t. We multiply that by rho of Shiri and I. This is the instantaneous probability that the game will be terminated by Shiri and me at that time. We multiply that by x of Shiri and me. This is our payoff, conditional that we take the integral, we take the summation of all subsets. This is our conditional payoff if we stop at time t to the integral over time. This is our yes.
That's to be sure. So, if, for example, the probability at each instantaneous time, the probability is positive for me to start, is it correct that the probability that I press the button before any epsilon is 1?
No.
No?
No.
Each instantaneous is positive, let's say above epsilon. So the probability, if you take the integral, it's 1, it's a plot.
Suppose you press the button, only you press the button, it's probability half at any time instance. Probability with u, because u is 1.
So it doesn't mean that the game stops, but it means that probability 1, I press the button. It's
No.
positive at each instant.
No.
Even at this.
Yeah, it's not a geometric distribution.
Yeah.
Okay, you essentially have here you press the button with probability 1/2 in every time instance.
Yeah.
So you put in an interval of length 1, you press the button with probability 1/2. In an interval with probability with length 1/2, you press the button with probability 1/4. Essentially something like that. Okay.
So
I understand that they don't understand it. Okay.
if the probability is 1, it's still not certain that you will put it on.
Right. If you stop with probability 1, no, you press it or push the button. It's not true that the game will terminate because we have a termination rate.
I'm talking about the probability.
That's what I asked. Yes. Probability of pushing the button is as much as that.
You said you multiply by the length of the interval, it's 1, it's what is not 1.
So if you push the button with probability 1, push the button. Okay, so the button will be pushed, and therefore you will be included in the S. Okay, for sure. Okay, but if you press the button with probability 1/2, then at every time instance, you are there only with probability 1/2.
It's independent.
Maybe I can try to frame it.
Yeah.
You can take the profile of control and translate it into one control. One control that says with what probability you push each, but there are many buttons, one for each button.
Yeah.
And there is a probability distribution over the set of condition.
Yes.
So you take this control and integrate it.
Yes, exactly. Exactly what we do. Okay. So we have each one of us as a control, whether to press or not. This defines, so on the entries of the matrix, this defines a control, which says that which is the product of all those reports. This is the probability that each entry will be reached in each time instance. Okay. Right? So if you press the button with probability 1/2, and only you press the button, then in each time instance, with probability 1/2, we all continue, with probability 1/2, only you stop. Only you press the button. Okay. And then to calculate the payoff, what we do, we multiply this 1/2 by the rho of what happens, what is the rho, the termination rate if you stop alone. We multiply it by the payoff, and we integrate it over time. So it does not mean that the game will not necessarily stop at time 1 because there is a termination rates. Okay. And you will press the button half the time. Okay, so yes, essentially you will press the button half the time.
So the rows are of the players that actually push the button or push the button with positive probability?
So you press the button with probability 1/2 and I press the button with probability. The probability 1/4, I press alone. The probability 1/4, you press alone. The probability 1/4, we press together.
And the row which
The row will be probability 1/4, I press alone, and it's my row. The 1/4, press alone, it's your row. Probability 1/4, we press together, it's the row.
For termination rate 1.
Okay, no. So the termination rate 1 is the game, and then we have counted the sum. Termination rate will be bounded from
And then you have
no, termination rate infinity.
in probability 1.
Yeah, so you mean termination rate infinity? The answer is no, we will not allow. Termination rates will be bounded from above and from below.
No, but nobody pushes the button, termination is 0.
0, yes. Okay. So here I emphasize the word control because I define control in behavior control by mixtures. Why? Why didn't I define a control to give a pure function that tells me when to push the button? Makes more sense. Okay. So let me explain why. Because if we define controls as pure structure, as pure sequences, pure functions, then the value will not exist.
So
Okay.
I'm supposed to observe the mixed behavior of others.
Yes. Yes. We observe the mixed behavior of others. Because if we observe the pure behavior, even in a two-player zero-sum game, the value will not exist. This is the second thing that we like to take from this talk. Okay, an example of a game in continuous time where when we have two controls, the value does not exist.
This is a problem.
Great. I'm back. In a moment. Okay, so this is our next set of slides. So let's take two-player game. Stopping game, zero sum, payoffs are constant, no information. Only the probability space is treated. Okay, so essentially player 1 wants that one of them stops alone. Player 2 wants either the game never to stop or that they stop. Now, what is the value of the game in discrete time? Question to the audience.
Matching penny.
It is like matching pennies, but it is a stopping game, right? So once at least one player stops, the game terminates. Almost half. It's actually twice. Okay? So the value is twice. Yeah, and an optimal strategy. So clearly the value is both. Why is it? It is 1 because player 1 can guarantee 1 minus epsilon. How? She stops at every time with probability epsilon. This means that eventually she will stop. But what is the probability that player 2 can stop with her? At most epsilon. And therefore, only one player will stop alone with probability 1 minus epsilon. So the value is at least 1 minus epsilon, probability epsilon, the value is 1. Okay? Good. So I surprised you at least. Omer, I surprised once.
No, but it's this.
Okay. Now, what is the value in continuous time? As a standard stopping game.
0, I guess. Almost.
To a constant factor.
No. up to an infinite factor.
Absolute rate epsilon.
No, here this is a standard game, yes. And what is the optimal strategy of player one? Here it is zero optimal. It is stop at a uniformly random time. Okay, because player one wants to stop, but he wants to hide the time in which he stops so that player two cannot stop. So you choose randomly. Stop at the random time in our class according to some continuous system. And it continues.
So it's one minus epsilon.
No, continues. So player two cannot, yes, only with probability zero, she can stop together with player one, and therefore the value, this is a standard stopping game, the value is one. Okay. So now we add the termination rates. Make the example more interesting. We add termination rates. So now the termination rate is constant. Okay, so that it's the constant one, so that the game is simple. And suppose that I actually choose a mixture.
The termination rate depends on who, right?
Yes, but here the termination rate is constant. Whoever pushes me alone, you alone, both of us, the termination rate is the same. It doesn't really matter. Suppose it is the same. And suppose that each one of us can choose the mixture, right? The probability by which he or she stops in every time. Not a pure mix. What is the value of this game? Now it's 1/2. Almost. Factor of 2. It's still 1. But yes, exactly. This was the answer for it. Oh, yes. Press with probability epsilon at every time instance. So the game will eventually stop. But I stop with probability epsilon. So if at a given time you stop, then with probability 1 minus epsilon we are here, and with probability epsilon we are here. And if not, then we will stop. And if you do not continue, then we stop here. So anyway, with high probability, we stop by a single player.
Some probability epsilon is always the right.
Yes. That's true. Okay. Now let's look at the same game with termination rates, but now, as you wanted, the players actually choose a pure control. They can choose randomly to control, but they choose a pure control. Zero. Value here now is 0.
By induction,
But
This is not a restriction, if I have randomization.
Okay, but this is what I say. So suppose that players choose randomly a pure control. I ask, what is the value of this game?
They mean choose randomization.
So you should, at the beginning of the game, right? I define the strategy as what? We partition time, and then in each time interval, as a function of what happened before, we choose a mix control, which is 0, 1 value, interval 0, 1 value. Suppose that at the beginning of each time interval, I choose a pure control, that is a pure function, When do I press the button and when I do not press the button? Maybe you will want to stop immediately, but if you stop immediately, then I will also stop together with you, and then the game will eventually stop and we will stop together, and the payoff will be, for you, will be 0. So you want to hide the time in which you stop so that I cannot push the button in the same time that you push the button.
once he pushes the button, I see it, and then epsilon after I can also.
You see it only at the end of the game.
So just to be clear, what you assume here is that the values are not in the interval, but either 0 or 1.
Exactly, but you can choose randomly your behavior in each time interval.
What do you mean by random?
Randomly meaning that at the beginning of each interval, you need to choose the set of time you're going to press the button in the next time interval. So you can choose this set of times by flipping a coin. You have several possibilities. Probably 1/3 you choose this one, probably 1/3 this one.
It's like a behavioral pattern.
And really behavioral stuff.
Maybe I missed something. I think it's still one because you can just take the same stuff. You take a random number between 0 and infinity, and then press the button at that time for a duration of 1.
Yeah. Okay, maybe this is possible. But unfortunately, no, the value does not exist. So in this game, when we restrict player to control pure, the value does not exist.
That's not.
Okay, let me convince you that this is true.
So just the technicality, it's not zero-sum because continue forever is 0-0.
Change the continue forever to 0-1 to make it 0. It doesn't.
It still says observed realization, you know, it's actually.
But that is
Think you just formulate it differently or to do different.
so. No, the question is whether the controls can be pure. And what I say here, the controls cannot be. They can be pure, but then there is non-existence of the pure.
No, but I thought that what you say differently just for convenience. What you really mean is that what we observe is the difference between the two models.
No. So what I mean is that controls, suppose the controls are pure. So they are fine. So in each, the strategy is divide time.
Oh, but you see the control of them.
Yes, see the control of the other. Okay, so I define the time intervals. At the beginning of each interval, I see the controls of the others, the control of the other in the previous time intervals, and then I choose my pure control. Then I see her pure control, and I choose my pure control for the next time interval.
But what if I chose mixed control in the next interval, but I only observe the realizations? Is that the same as what you're saying now?
You suppose you choose.
I only observe past realizations, but I choose a number between 0 and 1. Then this number is realized. Is that the same thing?
So the question is, what does it mean that the outcome is realized? Suppose you choose that in some time interval, press the button, you position 1/2. This is your choice. Now, so what you suggest is that eventually, at the end of the interval, we will actually see a realization of a random set in this time interval that has measured 1/2, which is when I press the button, right? A random set. What does it mean, realization of 1/2, a constant 1/2?
I thought it's either me pushing the button or not pushing the button.
No, we do it IID. Every time instance, you either push it or do not. If you want it to be 1/2 constant 1 and 1/2 constant 0, right? So you have a random choice of a pure control. This is what I allow. I do not allow IID in time in continuous time. This I do not allow. Because this is doesn't have you cannot from that you cannot select a realization such a pure realization.
There's assume an equilibrium, then assume that each player knows the partition of that.
Yeah.
So they can make a much finer partition.
Yeah, exactly. Exactly. So indeed the value does not exist because the max mean value is 0. Player 1 cannot be anything here, neither can player 2. So to convince you that this game does not have a value, I will present the following game, which is a game played by two players, Aqua and Bar. And Aqua should randomly choose a measurable function from 0, 1 to two elements, A and B. Press or not press the button.
This then is big meaning, mystical meaning.
And
Search the web, find it. Aqua chooses should select a measurable function 0, 1 maybe, and Bard should guess its function. So how the game runs, Aqua selects a measurable function f from the product 0, 1 plus 0, 1 to b. So she chooses, she randomly chooses, so the third coordinate is theta, is the pointer, and the second coordinate is the t, the actual value of the function. Then nature chooses the third coordinate uniformly, according to the uniform distribution. Then Bard observes f. She observes the mixed action of the random choice, but not the omega of the Q selection. And she should guess f of omega, okay, the section f of omega. How? So Bard, she provides a function g, it's her yes, and eventually we'll compare g and f of omega. How does she create G? She selects a partition of the unit interval, sub-intervals, right? We have non-anticipating strategies of delay. And then for each k, at the beginning, she first determines G on the time interval, on the interval tk, dk plus 1, and then nature reveals f of omega in the last interval. So this is exactly what we had before. The payoff is the Borel measurable, the big measure of the several times in which Bard gets to play. So this is essentially the game we had before, where Aqua is player 1 and Bard is player 2. And the question is whether what is the value of this game? So Bard min-max value is equal to 1. So Bard can correctly guess f omega. And the proof is not difficult. Losing theorem. They also has a lemma. Losing theorem says that no, so what I know is maybe you can prove it with the Vega theorem, but Lucid theorem says that every measurable function can be approximated on a compact set with that has a measure of at least 196. So Lucid. So this is okay. So if we have a measurable function, then we can find a compact subset with a value which approximates everything. It's the very measure with at least 1 minus epsilon, such that on this compact set, our function is f is continuous. Here we have only a and b. Our function is two-valued, meaning that continuity is relatively constant. So this is that if you saw, so we first will restrict ourselves to this compact set, which is very large, and then if we divide our time to find enough pieces, then when I see the constant value in the short interval, I know what is the constant value in the next 14. That's the. So anyway, this game does not have a value. I hope you put that as well. The three-player example, counter example, and this example, this game that does not have a value. So I glad I could surprise see. Okay, so now we have 4 minutes exactly for what we do. Now I think it's good because
Because that's splendid.
yeah, I have 2 weeks ago. So 2 weeks ago there was no on the theorem. Now there are because 2 weeks ago it was still gapless. Now it is with a gap. So the statement that we would like to prove is that every multiplayer stocking game with termination rates, if the termination rates are bounded from above, okay, they cannot be infinity because if they are infinity, it's like a stocking game. They are also bounded from below, because if they get 0, it means we have another entry where no.
There are conditions. Each condition is termination rate.
But the termination rate is not constant.
The rates themselves,
They change over time and like, wow. Okay, so but this is actually this doesn't matter if they change or not, it's the same thing. So we would like to prove that in such a case, an epsilon-equilibrium always exists. Okay, so now the small gap, but as we know, those small gaps are always closed, but maybe the people unpublished. So what we do know is, suppose there is no omega. Okay, so no incomplete information, then all processes are simply function of time. Then there is no problem, and indeed an epsilon-equilibrium exists. So the counter example that we had cannot happen in continuous time under our termination rate assumption. But what happens if we do have incomplete information, we have the filtration and omega, then this is still not. That's it. Questions?
Is time continuous? Otherwise, how can we talk about it?
What do you mean? I have formulas.
Are chaos continuous?
Yeah, I mean,
In the world, real world.
It's much good.
do we have rationality? I mean, do players know the game? Like, we make so many assumptions, I mean, impractical assumptions that make all of our papers not related